Hey guys, this is Mr. Welch doing a little bit of help or some basic instruction for 2.7 here in our Algebra 2 notes. And what we're working with here is graphing absolute value functions. That's loud. Absolute value functions in two dimensions, okay? And so when we talk about absolute value functions and how we graph them in two dimensions, a couple things that we have to acknowledge. We learned about absolute value back in the day that when we talk about the absolute value of, say, 3 or the absolute value of -3, that because it's considered a measurement from the position of 0, that these would both say that they are 3 units from 0, that the negative sign inside the absolute value is removed in order to measure a physical distance. Okay, so let's think about it. How far are you from 0? Direction doesn't matter, if you will. It has to do with what's called the magnitude of a vector. Okay, and so something that we learn in maybe a physics course, we talk about vectors versus scalar values, and that's an application that we would see that in. In terms of our absolute values that we're going to talk about graphing in two dimensions, what we're going to do is we're going to have a basic or a parent function. And our basic format is y equals a times the absolute value of x minus h, close our absolute value, plus k. Sometimes this is referred to as a vertex form of the equation. And we're going to talk about why it looks this way and what special information it gives to us. Okay? In a graph, okay, of an absolute value function, we're going to learn that because of the negative nature and how negatives are canceled in our absolute value, that we end up with these V shapes, okay? And a couple things that we're going to want to acknowledge. This point right here looks like a special point. It's the turnaround point for the graph. So that's something that we might want to talk about. It's commonly referred to as the vertex. And the vertex, if you want to know where it exists at the point HK. This is an XY ordered pair, but it's something that can be found by looking closely at our formula. And we'll look at some examples here in a second. But the vertex is that turnaround point. The next thing we want to talk about, this A, it sits in the position that a slope would sit if it was just a straight line. This isn't a straight line, but that A does give us some information. It is the slope of the right-hand side of our graph, which means that if I go up A units, let's call that A, I would go over 1 unit. So if slope is 3, I go up 3 over 1. If A is 2/3, I could say I go up 2 over 3 and create my graph from that. So let's look at some basic ideas. The most basic absolute value graph is just y equals the absolute value of x. This is actually called the parent function. And as we create the image here, we look and we notice that the h appears to be missing. Well, what number could I subtract without affecting x? The answer would be 0. And what number could I add without affecting x? Again, it would be 0. Then we'd look and say, well, what's the number out here? Well, when there's no number sitting in front, when we look at the slope and we don't see a number, we default to consider that a 1. Meaning I would go up 1 over 1, put a dot, and that would be my right-hand side. Because absolute value functions are symmetric around their vertex, I could do the same thing to the left. And this is what we call the parent function of an absolute value. It's a V shape, it's facing upward as it opens. The slope is a rise and run of 1, and its vertex is at 0, 0. Let's look at let's look at another specific example that might give you some better ideas of how this is really going to work. X minus 2 plus, let's say, 1. If I were to produce this graph, okay, I need to recognize that this -2 and this +1, it's like I moved the whole graph. In fact, we call it translation. This has been translated. Okay, now if I want to talk about determining h and k, we have to remember that the formula says x minus h. It doesn't say x plus h, it says x minus h. So that means this minus is a built-in. Okay, it is part of the formula. It's a built-in, okay? So that negative there, it's part of the equation. It's not part of the number 2. So when I say my vertex, we would say that it is a positive 2, because that's what's being subtracted. And then I want to say what's being added out here. Well, that would be a 1. So I can go to 2, 1, and I can put my vertex right there. Then I want to build my slope. Okay, the slope for the right-hand side is up 2 over 3. So I'm going to go up 1, 2, and over 1, 2, 3. Put a dot, and there's the right-hand side. Forgive me for a little sloppiness. If I go up 1, 2, and over 1, 2, 3, I'd be about there. And again, forgive a little sloppiness, but there's my graph. The bigger this number is, this 2/3, if I get it bigger than 1, the graph is going to get really steep. If I get a number less than 1, it's going to fatten out. And then the only other thing I can really do in terms of the graph is turn this slope into a negative, which would flip it upside down. Let's look at one last example, and I think you'll be pretty comfortable with this idea of how do we create these graphs. And in the homework, I'll show you how to do that on a graphing calculator as well. It's not a perfect solution. It takes just as long to get it into the calculator as it does to produce the graph, but I understand if some of you are big fans of trying to do it by calculator or technology. So let's look at y equals negative 1/2 absolute value of x plus 1 minus 3. First thing I always want to do is find the vertex. Okay. Now, when we talked about it over here, we said that this negative is built into the problem. It's not part of the number. I come over here, and I notice there's not a minus sign anymore. What happened to it? If we remember that x minus a negative 1 is the same thing as x plus 1, then there's our built-in negative, and what are we subtracting from x? A negative 1. Well, I look out here. I don't see the plus 3. But if I remember that minus 3 is the same as plus a negative 3, then that should work as well. And so I can put my negative 3 here. Let's talk about a general rule. Whenever the number is coming from a grouping with x, like these, we're going to switch the sign when we pull that information out. But a number that's simply added or subtracted at the end, we will leave it the way that it is. So we're switching the x, we're leaving the other the same as a general rule for finding the vertex. So I go to negative 1 down to negative 3, put a dot. The slope of my right-hand side in this problem is negative 1/2. That means I need to go down 1 and over 2. So down 1 over 2. This is going to force my v to be upside down. I go down 1 over 2 to the other side as well. And there's my upside down v that we create when we have a negative slope. Hopefully this helps you have an idea and understanding of how we shift it around and then create the slope from there. Good luck, and we'll see you in class.